Hey everyone, we have Jude Nelson, a research scientist at Stacks Foundation. He'll be doing a talk around Blockstack STX mining operations, hardware and security requirements. And I'll let him take it from here.
Hey everyone, my name is Jude. I'm a research scientist at Stacks Foundation, and we're talking about how mining works in Blockstack. So before I begin, just a few assumptions I've made about the audience. I'm assuming that the audience knows how blockchains work at a high level. I'm also assuming that they have some familiarity with how Bitcoin transactions work and what they do, what they are. Possibly if you've sent a Bitcoin transaction before. I'm going to assume that you know what I mean when I say the word miner in the context of blockchains. And I'm going to assume that you know what mining pools are. And I'm also going to assume that the audience understands how blocks are produced in a blockchain and some of the challenges inherent in doing so. That said, let's talk about mining in Stacks 2.0. So I have some good news. The only thing you need to do to mine a block in Stacks 2.0 is to send a Bitcoin transaction. This is true for both of the consensus protocols the system supports, proof of transfer and proof of burn. And it's great from a mining perspective, as far as mining perspectives go, in that it's much greener than the alternative because the energy consumption required to make a Bitcoin transaction is minuscule. Because mining is based around sending Bitcoin transactions, you get a lot of infrastructure support for free. The system is air gap ready. You can make a transaction offline and send it later. And it's browser ready. You could use just your web browser to mine blocks if you wanted to, because you can build a miner client completely in JavaScript. You can even do so by using a hardware wallet that already exists for the purposes of sending Bitcoin transactions. So that said, there's two ways to mine in the Stacks 2.0 blockchain. There's solo mining, where you and you alone are responsible for sending the Bitcoin via proof of transfer or proof of burn and participating in the block race and producing a block and announcing a block to the peer network. And there's also a native support for pooled mining, where instead of doing the work of producing a block and sending it, you simply contribute some Bitcoin towards another miner's block in the Bitcoin mempool. And if that block wins, you automatically receive a portion of that Stacks block's coin base. And this is built in natively into the system and described in SIP 001. So in order to begin mining on the Stacks blockchain, you'll need three things. You'll need a fully synchronized Stacks node that you trust that's online. You'll need a fully synchronized Bitcoin node that you trust and is online. And you'll need a program to package transactions into blocks, possibly on a separate computer, possibly on the same computer. It depends on your setup. And this will be the mining program. So high level, here's what the anatomy of a Stacks blockchain epoch looks like. So here's what a miner has to do if you're doing solo mining. So when you produce a Stacks block right here in the center, in order to do so, you have to send at least a few transactions to the Bitcoin chain. You need to send what's called a verifiable random function public key, or a VRF public key, embedded inside of a Bitcoin transaction, marked in red, and it must be confirmed before you begin mining. And also there has to be some parent block out there somewhere that you're building on top of, and that's the transaction marked in blue. You have to know what this transaction is. You don't send it yourself, but you just need to reference it in the transaction that you will send to mine your block. And to actually mine a block, you send this transaction here in gray that references these two other transactions. And if you win, you produce the winning Stacks block data right here, as well as a tail of microblocks that are tacked onto this anchored block afterwards. The act of producing this winning block requires you to know about the ancestral Stacks block here with these parent block linkages. So broadly speaking, your tenure as a Stacks miner during one epoch of the system runs in 3 steps. You set up the VRF so that it can do a cryptographic sortation to potentially select you. If your block commit transaction is selected through cryptographic sortation as described in the previous talk, then you can go ahead and produce your block. You can go ahead and announce it to the peer network. And then once it's announced, you can go ahead and start mining microblocks for as long as there are no other sortations that have happened. See, once the next sortation happens in gray right here, your tenure ends and the next person gets to produce their block in their microblock stream. So breaking this down in terms of what happens with your Stacks node and your Bitcoin node and your miner program, the system works as follows. You first got to generate your VRF keys. So the VRF keys is a public key and a private key. It's an ED25519 key. So nothing special there, just run of the mill. You have to sign and send a Bitcoin transaction that includes the VRF public key inside of it. And this is a security sensitive operation here. And once you have your transaction, you can go ahead and broadcast it to the Bitcoin network via your trusted Bitcoin node. And eventually it should confirm. Once it confirms, you ask your Stacks node, hey, did this transaction get included into your view of the network? Because in Stacks we have POX, and POX consensus is dependent on other Stacks blocks already being known to the Stacks node. So you will need to also ask the Stacks node whether or not your VRF key shows up in the same POX fork as the canonical chain. That should be the case if everything is working normally. No further work should be required from you. But once that happens, you can confirm that transaction has been accepted. Then you proceed to get the tip of the chain that you want to mine off of. So usually you just ask the Stacks node via its RESTful API, like, hey, what's the current VRF seed? So the thing you have to do the verifiable random function proof over, just an opaque string, nothing really fancy happening there, as well as the best chain tip. So which block is going to be your parent block or the tip of the canonical chain. Once you have these two pieces of information, you use that VRF private key you generated back here to make a VRF proof, to show that you're making some randomness, you're introducing randomness into the verifiable random function that powers cryptographic sortition, and you're doing so in a way that could only have been done by you. And again, the areas in red are security sensitive operations that we'll discuss after this here. So step 2, mining a block. So we have our private key, our VRF private key. We have the best chain tip we got from the Stacks node, and now we have this VRF proof. So now we have enough information to make a block template. So here's how we do that. We ask our trusted Stacks node to scan its mempool and produce an anchored block for us. Now it's pre-populated with all the transactions applied, but it doesn't have all the header information. Once we have that information, we can go ahead and combine the header with the produce Stacks block together, and we can hash it to produce a block hash and stuff that hash into a signed Bitcoin transaction encoding a block commit, and then broadcast that transaction to the Bitcoin network. This is the act of actually mining the block. You attach some Bitcoin in this that you either provably destroy through proof of burn, or you send to the proper reward set, which you learned in this best tip information here from the Stacks chain. Now that transaction should eventually confirm, and once it does, you can ask the Stacks node, hey, did this transaction get incorporated into the chain? And if so, did I win? And if you didn't win, you do all this over again. But if you did win, then hooray, you're going to get some stacks. You can go ahead and broadcast your block to the Stacks network, and the Stacks node will take care of doing that for you. So once you've mined the block, you now have a window of time between now when your block got selected via the arriving Bitcoin block and when the next Bitcoin block gets discovered, because that will contain enough information to do the next sortition. So in that approximately 10 minutes of time, you have an opportunity to produce microblocks. So you start out with your VRF private key from step 1. You have your best of information, you have your VRF proof, and you also have a microblock private key. This microblock private key you generate and incorporate the hash of the public key back in step 2 here when you're making the block template. But you use this private key now to do the following steps over and over again. You ask your Stacks node to scan the mempool and make you a microblock template, which you can then sign with that microblock private key and then broadcast to the Stacks network. You just keep doing this over and over again until either another Bitcoin block arrives and your tenure ends, or until you run out of block space, in which case you can't keep adding things on. They'll just get ignored. The only security sensitive task in this part of the mining tenure is simply signing and sending off these microblocks using this microblock private key that you announce as part of your Stacks block. So that's solo mining. Now we also support pooled mining natively in the protocol, and it's built in. Like there's no extra pool operation work to happen because it's built in such a way that it happens in a decentralized, coordination-free manner. So anyone in the world, all they need is access to the Bitcoin mempool, and in doing so, they can scan the mempool and find any pending block commits that are about to be mined, and they can throw some Bitcoin towards it. And in doing so, boost the aggregate amount of Bitcoin committed towards that particular block. So all the poolers, if that block wins, will get a portion of the Coinbase of the block that got selected. And this all happens without the block producers, it all happens without the solo miners' knowledge, and it all happens without the poolers' knowledge. The only communication channel that exists between any of these is simply the Bitcoin mempool. So here's an example. Suppose Alice is a solo miner, and suppose that she sends a block commit for 5 Bitcoins. And then suppose that Bob and Charlie are pooled miners. They don't know each other directly. They don't even know Alice, but they do see Alice's block commit transaction in the Bitcoin mempool. So what Bob and Charlie can both do is send block support transactions that contain the hash of Alice's key, as well as some Bitcoin for them that they're contributing as part of weighing Alice's block for consideration in the cryptographic sortition. So Bob can send 1 Bitcoin and Charlie can send 2 Bitcoin. So now Alice's block has an aggregate 8 Bitcoin weight now in the upcoming block sortition. So if Alice, Bob, and Charlie's transactions all get mined in the same block and processed in the same sortition, which is what normally happens, then if Alice's block wins, then Alice will get awarded 67.5% of the Coinbase, or 5/8 of it, since she contributed 5 of the 8 total Bitcoins. And she also gets all the transaction fees for her epoch. And Bob will get 12.5% of the Coinbase for his 1 Bitcoin contribution, and Charlie will get 25% of the Coinbase for his 2 Bitcoin contribution. So in pooled mining, here's how this works from a protocol standpoint. What your miner program does is it scans the Bitcoin mempool for new transactions, and then it looks for ones that just happen to look like block commit transactions. To verify that they're potentially valid block commit transactions, you just ask your Stacks node, hey, will these be accepted if they are in fact committed in the next Bitcoin block? And your Stacks node will tell you yes or no, or it'll just give you a filtered list of the ones that are potentially selectable. So from there, you can sign and send block support transactions to the Bitcoin chain. And then once they confirm, you can ask your Stacks node, hey, did the block you tried to support win? And if so, you can expect some Stacks tokens later on when the Coinbase matures. So in these 2 mining modes, we've seen 4 security sensitive operations to be aware of. And 3 of them are just signing Bitcoin transactions. Either sending a transaction with a VRF public key, sending a transaction with a block commit with the hash of the block you intend to mine, or you're sending a transaction with a hash of a block that you are intending to support and try to get selected to the sortition algorithm. In the 4th case, you're just signing a microblock using a private key that only lives as long as your miner tenure. The first 3 tasks, though, that can be done today with a hardware wallet using any and all off-the-shelf libraries and tools for signing Bitcoin transactions. And the 4th one, while it does not have the same level of support from the existing tooling out there because it's not a Bitcoin transaction, it is using a short-lived private key. So you don't have to worry about that key being exposed once you're done with it. And also microblock mining, if you're really paranoid, is a totally optional feature you don't have to participate in, but it is profitable to do so. So I encourage miners everywhere to do it. So that said, let's go into the mining hardware requirements. This is true for both pooled miners and for solo miners, by the way. The first thing you need is a trusted Bitcoin node that you and your Stacks node can talk to. Because recall, Stacks nodes read the Bitcoin chain to determine the sequence of transactions that make up all the sortitions that in turn select the blocks that make up the Stacks chain. So you will use your Bitcoin node for that, as well as for keeping track of all of your mining UTXOs. And if you're doing pooled mining, for maintaining the mempool for you to scan so you can see any other outstanding block commit transactions that are imminently mineable. You also use the Bitcoin node to determine if your on-chain transactions are confirmed or not. And running a Bitcoin node, well, I mean, if you just go to bitcoin.org, they'll tell you the minimum system requirements, but you only need about 512 megs of RAM and maybe 300 gigs of disk space, which is eminently attainable these days. Like you can use a beefy Raspberry Pi, for example, to run a Bitcoin node. You also need a trusted Stacks node that you can talk to. And this Stacks node is going to be producing the blocks and the microblocks for you using its own mempool. So it needs to be connected to the internet and seeing any unconfirmed transactions. And it's also going to be telling you about the state of the chain, like the reward set you have to commit to, the VRF proof you have to generate, the seed you have to generate your proof over. And its system requirements are pretty similar to Bitcoin's. Its chain state grows at a linear pace. The maximum data per epoch is 2 megabytes instead of Bitcoin's 4 if you have SegWit turned on. But yeah, like similarly, a beefy Raspberry Pi with an external hard disk should be adequate. Third, you're going to need a mining program. We're still working on these, by the way. Any and all collaborations on this will be welcome. Right now, our testnet node just has a built-in miner. It can run as a command line tool. It can be running inside your web browser, talking to your Bitcoin and Stacks nodes, etc. And it can also be on a separate computer. You can set up your Bitcoin and Stacks node on your home network on Raspberry Pis or on a home server, and this can just run on your laptop, for example. And it's highly recommended, but not required, that you have a hardware wallet for storing your Bitcoins, because you'll use your hardware wallet for actually signing and sending those Bitcoin transactions. And that's great because it makes it much harder for someone who's in your network to steal your Bitcoins that you're intending to use for mining. So those are the requirements. So here are some nice non-requirements I just want to bring your attention to. You don't need a public IP address to be a miner. You can do all of this at home. All of this works behind a NAT. You can have a firewall. All it needs is just a downstream connection for talking to the peer network and receiving blocks and transactions from the Bitcoin network and the Stacks network, as well as the ability to just connect to other public nodes so you can relay your blocks and transactions to them instead. You don't need a lot of electricity. This is not like Bitcoin or Ethereum. All you're doing is sending a transaction to mine a block, which just takes negligible power. I mean, you could probably plug your Raspberry Pis into solar panels and they'll work just fine. You don't need a very high-speed internet connection. You don't need a multi-homed relay network. I mean, they're nice to have. I'm not going to say no to that if someone offers that to me. But strictly speaking, and in a general sense, mining a Stacks block isn't a race. All you have to do is get your transaction into the mempool before the next Bitcoin block is mined. So you have 10 minutes, 10 whole minutes to get that block commit mined. You don't have to worry about racing someone else to do it. And you don't need a particularly high-speed internet connection to do this. Stacks 2.0 epochs, like I said earlier, are just 2 megabytes of data every 10 minutes, which is comparable to what Bitcoin is. You should be able to stream both of these on a 4G connection with enough, that's not too oversubscribed. I don't recommend bootstrapping off of that, but you could sustain the network on this. So with this setup, with these computers for your Stacks nodes and your Bitcoin node and your mining software, what can go wrong if someone gets into them and hacks them? Suppose that the computer running your Stacks node gets hacked. The worst case scenario they can do is they can deny service. They can prevent you from mining by feeding you invalid data or just no data, causing you to make an invalid block or mine off of a fork that isn't the canonical fork. Similarly, if your Bitcoin node gets hacked, it's a little bit worse because they can not only give you bad information about, say, the state of your mining UTXOs, but also they can give your Stacks node bad information and cause it to get screwed up. So in order to fix this problem, you need to reset both your Bitcoin node and your Stacks node. And that takes more time and more energy to get fixed. If your miner gets hacked, it's a bit worse. The worst case scenario for you here is a coin theft, because the hacker can just steal your block reward once it matures, because they'll know your private key and they'll be able to spend your matured block reward as soon as it matures. Similarly, if your wallet gets hacked, and this should be a rare thing if you're using a hardware wallet, and one of the reasons why I highly recommend you use a hardware wallet, it's also a coin theft problem. They can steal your stash of Bitcoins that you intended to use to mine. So what about stacking? It's a similar task to mining. I'm going to save this for the next talk, though. That's going to be talked about by Zan when my talk is finished. But in terms of hardware requirements, it's basically the same thing. If you can set up a miner, you can set up a stacking rig. But it takes even less work because you're just sending a transaction once a month or so, or even less frequently than that. Cool. So that's mining in a nutshell with the setup and requirements. What about strategies? So I mentioned earlier that all your transactions hit the Bitcoin mempool, for example. And that means that everybody can see your mining transactions before they actually confirm. This is both a great and terrible thing. So what you should be doing if you're mining is you should be looking at the mempool regardless to try to see if other people are mining as well. And you should try to use replace by fee to upbid either your block commits Bitcoin, as well as to try to increase the fee so that there's an even higher and higher chance of the Bitcoin miner taking your block commit transaction into the next block. See, you and everybody else can see this, so eventually everyone will reach an equilibrium where they send the transactions at exactly the value that they think that they think will get them mined according to whatever private risk profile they have here. But you really do want your block commit to get mined to the next block, otherwise you risk getting your Stacks block orphaned, even if it is selected later on. Second strategy. You should consider sending block support transactions all the time. Like even if you're competing with other miners regularly, you can hedge your bets by sending even a small block support transaction, because if you lose the block race and you don't do this, you lose everything. Your Bitcoin are gone, but you don't get any stacks. By hedging your bets this way, by sending a block support to help your rival miners, it not only strengthens the chain, the canonical chain that you're all working on, by showing the world that, hey, there's a lot of Bitcoin moving around as a result of this chain being mined, but also it hedges your bets. You get some stacks, you get some fraction of the Coinbase later on if a rival miner's block happens to win the block race. And the third strategy I'd like you to keep in mind is you should really pace yourself when you're mining microblocks. You have a whole 10 minutes. You don't have to blast out all your microblocks in the first 30 seconds. And in fact, it's to your advantage to wait, because transactions are arriving all the time into the Stacks mempool, and you don't want to commit all your microblocks early lest you miss a high value transaction you could have mined by waiting. So it's good to just try to fill up that 10-minute window with your microblocks. It helps everyone, it helps make the system smoother for users because transactions confirm faster. You have no recourse if you happen to run out of microblock space because microblock streams are not allowed to fork. But otherwise, yeah, just be patient when mining them. There's a good chance you'll be able to pick up high-value transactions that come into the mempool intermittently. So that's mining strategies. Let's talk just a bit about transaction fees. So the fee system we use in Stacks 2.0 is based on a paper from Basu et al. In 2019 called Towards a Functional Fee Market in Cryptocurrencies. And unlike Ethereum and Bitcoin, the system implements a generalized Vickrey auction for block compute capacity. So a Vickrey auction is an auction where the second highest bid wins. And the nice thing about this from a game theory perspective is that it means that people are encouraged to bid their honest assessed value. There's no game they can play that gets them a better price than by being honest. A generalized Vickrey auction is where the K highest bid wins for some constant K here. And what you're bidding on here is the stacks per compute op rate. See, stacks blocks have capacity. It's not measured in bytes, but it is measured in some other unit that's based on the amount of bytes it takes up, the amount of I/O that the transaction does, the amount of CPU cycles the transactions all do. And that can be distilled into a single dimensional unit that's auctioned off. And that's what y'all are bidding on when you're sending transactions. Now, in the generalized Vickrey auction strategy described in this paper, transactions with lower bids than the K highest stacks compute op pay nothing. They're mined for free. But everyone who bids K or at the K highest rate or higher, they pay just the K highest rate. And in order to make sure the system works, miners must fill the bill to some constant F% full, where full here is like the number of stacks per compute op units must be F% of the total allowed amount of stacks of compute op units that are defined by the protocol. If they don't do this, if they mine a smaller block than F% here, then they have to pay a fill penalty, and that comes out of their Coinbase. So let's say you mine a block that's just half of F%. Well, then now you're getting a Coinbase that's half of what the Coinbase would have been otherwise. This encourages miners to make sure to fill up their block with as many transactions as they can get, even if they're low value transactions. And F and K here are protocol constants. They're not something that adjust dynamically. I encourage you all to read this paper by Basu et al. From 2019. It's actually pretty informative about how to do a decent stab at building a fee market for cryptocurrencies. Transaction fees are a little bit different as well in how they break down for their maturity and reward schedule. The Stacks transaction fees are paid out dependent on whether or not the transaction was mined in an anchor block whose hash is in the Bitcoin chain, or a microblock where it's streamed at the end of a Stacks block. If it's the former, if it's in an anchor block, the miner gets all the transaction fees. But if it's the latter, you actually have to pay both the current miner that produced that streamed block, as well as the next miner that confirms that stream of blocks. And the split for this is 40-60. So the miner that produces the anchor blocks gets 40% of the fees, and the miner that confirms them gets 60% of the fees. And this is not listed here, but this is based on a paper called Bitcoin NG from Usenix. I believe it was 2016, the annual technical conference from Cornell. They devised a similar system that behaves similarly to Bitcoin, but it uses this microblock scheme instead. And this is the result that they got at when they're trying to incentivize miners to operate without selfish mining. And we're just duplicating that result here. So speaking of maturity, the way that block maturity, reward maturity works is as follows. You don't get your Coinbases immediately. They actually have to be locked up for 240 stacks blocks before you can get them. And the reason for this is that we want miners to keep working on the chain after they've made their block. Otherwise, they could just double spend exchanges, for example, by just mining off the chain tip, mining conflicting blocks with the block that they produced over and over again. And because we have proof of transfer, we're particularly sensitive to this sort of behavior. So we want to make sure that miners are encouraged to keep working on the chain for at least as long as one prepare phase of proof of transfer, which right now is 240 stacks blocks. We don't want miners to attempt to reorg a prepare phase because that could that could make it so that an anchor block is not selected. And that in turn hurts everybody because then proof of transfer doesn't happen. Transaction fees don't mature at the same time as Coinbases. In fact, we're still toying with this number, but we're looking at trying to make it so transaction fees mature a month after they're mined, approximately. And the reason for this is that transaction fees can be very variable and they can be very high, in some cases higher than the Coinbase. There's a bunch of papers about what happens when this sort of phenomena happens. But the short end of it is, if your transaction fees get so high that they dwarf the Coinbase, miners stop being incentivized to work on the chain properly. Like they'll be petty compliant, they'll try to fight over high value transactions, and the chain quality suffers as a result. So it's to our advantage to try to make it so that at least high value transactions are unlocked later, because what it does is it creates a time discount for the monetary worth of those Stacks tokens, which in turn encourages miners to keep making progress on the blockchain in order to actually see that value. Because what we don't want is for miners to try to reorg the chain, fighting over high value transactions. We're still toying around with this. We're open to discussion on this. We really want to think about this thoroughly before we commit to a particular strategy. But I'm just telling you all where we're at right now on the design of the system. And the final thing about block maturity that I want to bring to y'all's attention is Coinbases for empty sortitions are paid forward. So it's entirely possible that a Bitcoin block can get mined that has no Stacks block commit transactions in it. And in fact, this can happen even naturally and under a rational actor model, because if Bitcoin transactions are so high that they're worth more than the Stacks Coinbase, then no one would ever want to mine. It's not profitable. So to fix this, we make it so that if there's gaps, if there's Bitcoin blocks that are missing Stacks blocks, then the next miner to produce the block can simply claim the Coinbases for those not mined Stacks blocks. So let's say, for example, that the Stacks chain chip hasn't advanced for 3 Bitcoin blocks. Then 3 Bitcoin blocks later, if a miner produces a Stacks block, they not only get their Coinbase, but they get 3 times the Coinbase rate. 3 times the Coinbase rate coming from the 3 Bitcoin blocks that they're spanning here. And this should make it so that it will always be eventually profitable to mine a Stacks block, even if Bitcoin fees, go through the roof like they have in the past. That's all I have on Stacks mining operations and Stacks token mechanics here. With that, I will take questions. I'll just go ahead and I'll tab over to the questions here. I see with one question, is there a Docker file to test the above Stacks mining concept? The best we can do for that is if you spin up a node on the testnet, it will automatically start mining blocks for you in the miner configuration, but there isn't yet a separate miner program that does this. We're actively working on this. So there's another question here. How can miners reliably calculate a Bitcoin commit if they cannot foresee the value of the Stacks tokens they might receive? That's a good question. So the reason miners mine at all really is because they believe the Stacks tokens are going to be valuable enough when they are obtained. If miners believe, so this really is a leap of faith here, and this is, by the way, this is true for all blockchains. Like Bitcoin locks up Bitcoin rewards for 100 blocks, for example. The reason here is less to do with trying to force some sort of market dynamic and more to do with just making sure that miners are always incentivized to keep working on the chain, or at least not getting in the way of the chain's advancement. Because even if the Stacks are not worth very much by the time they unlock, like something is better than nothing. And a miner that at least isn't mining isn't going to actively attack the system if they have a big Stacks reward coming for them later on. That's a really good question though. See another question here. Is there a link to the paper and perhaps SIP documentation somewhere? Yes, there is. You'll want to take a look at SIP 001 and SIP 007. Oh, I'm sorry. Are you talking about like other papers? I see that Escal has dropped a paper in here. Let me just quickly check which one this is. It's not loading for me, unfortunately. Oh, for Basu et al. Yeah, great. Believe that's on archive somewhere as well. I'll just type the name of the title in. This archive link should also work. And I did mention the Bitcoin NG paper. Let me go ahead and find that paper here. Oh, I'm sorry, it wasn't ATC, it was NSDI. There we go. Thanks, Shannon. Glad to be here.
Thanks, Jude. This was really great. So we're going to transition to Zan's talk within the next minute or two. Thanks so much.
Thanks.